So it's my pleasure to introduce Eva Darulova. Actually, I never asked if it's Darulova or Darulova. So, but hopefully it's one of the two.
Doesn't matter.
Okay, Eva Darulova from MPI for software systems, and besides being an excellent climber, Eva is also an excellent researcher doing a lot of interesting work in a variety of topics, and more recently focusing a little bit more on synthesis, and since many years ago been focusing a lot on uncertainties and try to make sense of errors in a lot of things in programming. And she did her PhD with Victor Kunchak at EPFL, and she's for the last, I believe, 5 years now, or 4 years. Actually.
5.5, yeah.
5.5, yeah. So she's been a professor at the Max Planck Institute. So without further ado, we all want to hear about synthesis with uncertainties.
Thanks, Loris, for the invitation and also the introduction. So the title is quite non-descriptive, and that's because I would like to talk about 3 different projects today that vaguely have something to do with synthesis and uncertainties, though each one of them in somewhat different ways. But these are 3 recent projects, and I haven't talked about them so much yet, also thanks to Corona, so that's what I want to talk to you today. So sorry that there is not this like one big story tying them all together. That said, if you get lost in one of them, then you can just start again for the next project. So let me start with the first one, sound approximation of numerical kernels. And the kernel that I will be using is this expression that computes the azimuth. And if you don't know, the azimuth is the angle between some point of interest given as a latitude and longitude and some reference direction, again, given as a latitude and longitude. So this expression may be used in some embedded system or some robotics application for navigation. Now you can derive this expression analytically using real numbers, but if you then actually want to implement it on some actual system, say an embedded system, well, then this is going to be difficult because the infinite precision reals cannot be straightforwardly or efficiently implemented on today's digital and fundamentally discrete hardware. So basically what we need to do is we need to approximate the real arithmetic and the corresponding computations, including the calls to sine, cosine, and atan, so that we can actually run our application on some embedded hardware, say. Now, each of these approximations is going to introduce some error. So we need to make sure that our overall results are still going to be good enough for our application. Now, all of these errors are actually not all that bad. And this is basically because many applications, especially in the embedded and robotics domain, are designed to be robust to some amount of noise, just because they have to work in a noisy environment anyway. And in particular, the inputs are usually not going to be infinitely precise, but they will come, say, from a sensor that has a limited precision anyway. Secondly, many such applications only need to work for a very restricted domain and don't have to work for, say, -infinity to infinity. So, for example, for our azimuth expression here, we could imagine that this would only have to work in a certain part of the world. So our latitudes and longitudes would be quite restricted. Now, this provides us with an opportunity because we may be able to use some coarser approximations and by doing so save resources. Now, in general, the more accurate we want our computation to be, the more we will have to pay in terms of resources. Put differently, if we can deliberately reduce our accuracy, we may be able to get, say, a faster implementation. Well, that's all great. But unfortunately, navigating the trade-off between accuracy and efficiency is hard, at least hard to do manually. So the first problem is that each individual approximation will introduce some individually, hopefully small error, but they will propagate and they will potentially magnify throughout the computation. So what we need are sound verification techniques that will allow us to compute an upper bound on the error at the end of the computation, so that we can tell whether a particular approximation is good enough for our context or not. Secondly, the space of possible approximations is huge, and we cannot possibly manually go through all of them. So in order to get actually efficient implementations, what we need are automated approximation techniques. And this is the first sense of synthesis that I'll talk about. Basically, we need tools that will synthesize these approximations for us fully automatically. So what I have been developing in the last 5 or so years is a tool that will allow you to basically take this expression and write it down as a real valued specification in this DSL. So you can basically just encode your arithmetic. You can provide the precondition that specifies the input domain, and you can provide a bound on the final result. So this plus minus notation means the absolute error on the result. So this is what we want to have satisfied. And then what can we do with this? So our tool that I have called Daisy can generate floating point implementations from this that are guaranteed to satisfy the error bound. But it's not just going to pick some uniform precision. Instead, it can choose, if possible, a mixed precision implementation. So it may, for example, for our particular error bound and particular application, find that the last few operations can be implemented in double precision, and the remaining ones have to be implemented in some higher precision. Now, if we didn't have such a tool, we would probably have to choose some higher precision just to be sure. And if we take that higher uniform precision implementation as a baseline, then the implementation that our tool can come up with automatically saves you around 15%. So that's sort of floating point arithmetic. That's the kind of stuff you could run on a regular computer. Now, what if you can actually run your implementation on an FPGA? Now, and suppose that the error bound that we need to satisfy doesn't actually have to be quite so tight. So we can tolerate a little bit more error. So this is great because then we can use fixed point arithmetic instead of floating points. And for those who are not familiar with fixed point arithmetic, this weird annotation here, this is quite specific to the particular FPGA that we are targeting. But basically, ultimately, what this is going to use is plain integer arithmetic to implement the decimal computations. Now, naturally, because we're then not going to use the floating point unit on all the automation that it provides, we need to do a little bit more effort at compile time in order to generate this code. So what we're generating here is the total bit length that we need in order to represent our computation with the desired accuracy. And the second number is the number of bits that have to be reserved for the integer part of our number so that we don't get overflow. So compared to a floating point unit, the floating points would determine these kind of integer bits. So the bits for the integer part dynamically, we now have to select them at compile time. Now, Daisy doesn't just select the precision of the arithmetic operation, but it also approximates the calls to the elementary function calls by polynomial approximations. And these polynomial approximations are specific to the particular domain. So they don't try to cover all of the input domains, not all of the part of the input domain that a regular library function would do, but it's going to be really focused on just the input domain that we have specified. So I'll tell you in a second how we actually do this, but just as an advertisement, with this, we can basically run our code in about half the time compared to sort of the off-the-shelf implementation using library functions and some default precision. So this really can buy you much, but it's not really straightforward to do by hand. And let me just give you a hint on, or a high-level explanation how we do this. And for this, I'll represent our function as an AST because I think it's a bit easier to explain. And the main challenge is, or let me first start with what we actually know how to do. So if you have just a single elementary function call, say a cosine function, then there is actually an algorithm that can compute the best polynomial approximation that satisfies some given error bound. So best in this case means the polynomial that will have the smallest approximation error. However, in order to apply this algorithm, we need to have the local bounds on that particular elementary function call. But the only thing we have is the total error bound on the result. And we have several elementary function calls to deal with and to account for. So basically what you can think of this total error bound, sorry?
Is the best, so when you talk about the best polynomial approximation, you're still working in reals at that point?
Yes, that's still in reals.
Okay.
Yeah, that's still in reals, and I'll just come to that just in a second. So basically we have this total error bound, and you can think of it as sort of a budget that we have in order to distribute that among the polynomial approximations and sort of the errors of the approximation with respect to the reals. And we also need some of the error budget for the actual finite precision implementation of the approximations and all of the arithmetic operations of the top level function as well. So there's a bit of a chicken and egg problem, because basically we need to know the approximation in order to compute the overall error bound, but we need the local bounds to be able to compute the approximation. We solve this in a sort of two-step process. So in a first step, we abstract over the elementary functions, and we kind of treat them as some kind of slightly special arithmetic operations. And we distribute our budget sort of globally on the top level nodes of our AST. Now, the idea why this makes sense and why this ultimately works is that the errors on the so due to the approximation of the elementary function calls, they should be relatively similar to the remaining operations, because otherwise they would dominate the overall error, and we could probably distribute the budget better. So now that we have distributed this budget sort of globally, we will then look into each elementary function call and take the budget that it was assigned to each function sort of locally and distribute it among the polynomial approximation, which we will compute with the Remes algorithm, and the actual implementation of that polynomial. So let me go through these two steps. And let's look first at the global error distribution. So the first thing we'll do is we'll try to find a uniform precision assignment in fixed point arithmetic. And remember, in fixed point arithmetic, we're assigning a number of bits that we have available. And if we're going to implement this on an FPGA, then we can in principle use any number of bits. So we could use 32, but we could also use 65 or 13 or what have you. So it turns out that for our particular error bound and application, a uniform precision assignment of 33 bits is enough to satisfy the error bound. And we can verify this with our static analysis that I'm just glancing over. So basically, we have an analysis that, given a precision assignment, can tell you, yes, your error bound is satisfied or not. Turns out we can do a little bit better than just this uniform precision assignments, and we can choose some operations that we will perform in lower precision. So for instance, we can choose to take half of the operations and perform them in 32 bits, or at least pretend as if the elementary function calls could be performed in 33 bits. Turns out this will not satisfy the error bound, so we will try the other half. This won't satisfy it either. So we will try to reduce at least a few of the operations. Now, in this case, this will actually satisfy the error bound. So we will try to repeat the process and try to lower the variables that we have just lowered even further. So it turns out that this is going to be the final mixed precision assignment that we can do at the sort of global level. So then we will interpret the 33 bits here basically as representing a rounding error, and we will use that rounding error as a local error budget to approximate the call to cosine. So we again have a error budget, and I'm just showing this sort of as an interval or as a line. And it's a priori not clear how much of this has to be allocated to the polynomial approximation and how much to the actual finite precision implementation, just because the search space is so complex and not really continuous. So what we do is we'll just so we will just divide the budget in half, and we'll use half for the polynomial approximation, on which we will then call the Remes algorithm finally to get a polynomial approximation. And then we will repeat the precision assignment that we've done before globally, now locally on the polynomial that we have just gotten. And then we will do a sort of refinement loop. We will try to split the error budget a little bit differently. We will repeat the process. And then we will use a static cost function to choose the implementation that heuristically we believe is going to be the fastest one. So for our polynomial, the finite precision implementation that will finally be generated looks like this. And you can see that some of the operations, for some reason, can be done in much lower precision than some of the others. And we will basically repeat this for all of the function calls that I'm eliding here. But basically, we will compute 7 approximations for the 7 elementary function calls. Now, this is implemented in our tool, and that is available on GitHub, which, yes, exactly. So if you want, you can try it out. Are there any questions before I continue?
So is there a way to just phrase this as a constraint solving problem in a theory? I don't know what the theory is.
So not really, because what Remes algorithm is doing is an iterative algorithm. So at least that part, I don't really see how you would phrase that.
Like the other part you did before, where you were finding this precision stuff. So
for floating point arithmetic, yes, indeed, that you could formulate that as a optimization problem, and there's actually a different tool called FPTuner that does exactly that. The flip side of that is that approach doesn't work for fixed point arithmetic, just because we don't have a very nice abstractions of fixed points that is continuous enough, and the optimization approach is also much slower.
Interesting. So what is on this one? So this is where you got. What was the improvement on this because of this?
So this ran in half the time.
Half the time. Okay.
Yeah.
So it looks like in this example, there are only 2 of the calls to sine and cos that are on an expression. The ones that call where the argument is d-ln.
Yep. And the other ones happen to be directly from the inputs, but that doesn't really change much for us.
So you're doing some sort of like interval approximation and then.
Exactly. So we propagate the intervals from ln 2 and ln 1. So we will have equally an interval for d-long. So we will know what the domain is that the elementary function calls have to work over.
And if you'd had like sine of cosine of x, would you run into problems, or it's just compositional and everything works out?
No, so that would actually work. So Remes algorithm works as long as your function is univariate. So if you just have sine cos of x, that's perfectly fine, and you could do exactly the same thing. As soon as you have more than just one variable, then this is not going to work anymore. Now, there are other polynomial approximations you could, I guess, fit into. Now, if it works, then we should use the best one, basically.
Mm-hmm.
All right, so that was the kernels. But, most programs don't consist of just kernels. And many programs will have loops. And the problem with loops, as you all probably know, is that the number of iterations may not be known. And in particular, if we want to analyze a floating point program, as the one that is shown here, we cannot just do simple unrolling. And the other problem is, even if the number of iterations was known, the current verification techniques are not particularly scalable, so you couldn't unroll it for many iterations. So usually what you do when you have a loop and you don't necessarily know the number of loop iterations, you'll find a loop invariant. And this is just a reminder in case there is someone who is not familiar with loop invariant. A loop invariant is a property that holds at loop entry and after every iteration. And we can prove, given such a property, we can prove by mathematical induction that it is implied by whatever was true before the loop. And we can, if we assume that it holds before the loop, after one loop iteration, it will hold on the newly assigned values of, in this case, x and y. So that means if you have such a property, just proving that it is indeed a loop invariant is not a difficult problem. The problem is that finding one, and finding one that is strong enough, so that it means especially that it satisfies the inductiveness condition, that is really the tricky part. And in general, there are techniques for finding loop invariants for specific program fragments. And the kind of specific loop invariants that we were looking at here are the ones that I'm showing here. So basically, we're looking for lower and upper bounds on the magnitudes of the variables. Now, these are, for instance, important in safety verification, where you want to show that your system is not reaching some unsafe state. But this is also a prerequisite so that we could bound rounding errors, because rounding errors depend directly on the magnitudes of expressions. Unfortunately, the simple loop invariant is usually not strong enough so that we could prove the inductiveness condition. So it turns out that the condition I'm showing here, this is actually a loop invariant, but it is not inductive. In order to make it inductive, we have to add a polynomial constraint so that we can actually prove that condition. And let me show you visually what this looks like. So the green box, that is the precondition, that's where we start from. The light blue lines are some concrete executions of the loop. The outer blue box, that's sort of the box constraint that we're originally after. And the polynomial constraint is the ellipsoid. And the tricky part is really finding this ellipsoid together with the interval constraints. So, well, I said the polynomial is the thing that we're after, but the constants, so basically we need to find the polynomial, so the coefficients of the polynomial, but the constants look awfully specific. So why is it 0.44 and not 4.5 or something else? Turns out the exact constants are not really important because there are many different invariants that all have this sort of ellipsoid shape that all satisfy the inductiveness condition. So we basically need to find one of them. That means we do not necessarily have to perform exact reasoning. And in fact, we're going to leverage this noisy nature of finite precision and of these particular loops to find one of these invariants. Ultimately, we would like to find the strongest one, so basically the smallest ellipsoid, but if we can't find the smallest one, we'll already be happy if we can just find one of them. All right, so we have used CGIS, counterexample guided inductive synthesis, with a couple of slightly different steps than sort of to the, well, that the standard approaches would use. So our generate step, so the first step will generate a candidate invariant that we will verify using SMT. If SMT says yes, the inductiveness condition is satisfied, then we have an invariant. If not, it will provide a counterexample from which we will try to generalize. So that's the basic CGIS loop. Now, obviously, so I'll tell you exactly how the individual steps work. But before that, I want to just make a note that some of the sort of standard domain, something like a conjunction of given predicates, doesn't work in our case, because what we need to generate are these coefficients. So basically, we would need to have predicates with all the possible polynomial coefficients. So that's not going to work in our case. So what we will do is we will start off, so we will initialize our search by just simulating the loop starting from the initial set. So basically we will start from our precondition and we'll just randomly sample a number of inputs and run the loop around 100 iterations, I think. Now, and we will collect the points that we will see during this execution. Now, these points are basically points that our invariant definitely has to cover because they appear in a concrete execution of the loop. So just to show this visually, the green box is the precondition from which we will sample, and then we will simulate the loop. So you can see that the samples, so the loop is going to, take a bit of a detour and then eventually, converge to some area or to some point. Now, the number of points that we generate by this is usually pretty large, so we will just compute the convex hull to reduce the number of points that we have to cover. And then on those points, we will fit a polynomial using, for example, just least squares. And this is going to give us this polynomial that looks, again, very noisy because there's very specific digits. And in fact, this is a little bit too specific. So what we want is to reduce some of the noise that comes just from our random sampling. And we found that just rounding the coefficients is enough to reduce some of this noise. So this is going to be our first candidate invariant, together with some interval constraints as well that I'm not showing here. So visually, the dashed line, that's the initial fit, and the rounding is going to make the ellipsoid a little bit larger, also to definitely cover all of the points. But it's also a little bit larger because we're rounding to some number of decimal digits. So this we will try to hand off to SMT, but unfortunately we found that just the floating point theory is not scalable enough, so that will take forever. But because we can use some of the, or we don't necessarily have to find exactly one particular unique invariant, we can use an abstraction of the real valued body. So what we will do is we will take our loop body, we will express it in SMT using the real valued theory and add an error term that we will compute with our usual accuracy analysis. So basically we'll over approximate the execution of the loop body, but we can then phrase the constraints using reals to the SMT solver.
Can you go back one slide? So here you said that you over approximate, but you're losing some points here as well. There's some blue that is outside the dotted curve.
Yes, but the curve that we will actually use as the candidate invariant is the outer one. So we always round such that we are covering all of the points that we have seen so far.
Got it. Okay.
Because otherwise we couldn't possibly prove that it is an inductive invariant.
Yeah, exactly.
All right, so we got around the problem with the slow floating point theory, so we'll just use the reals, which on paper has also a pretty bad complexity, but at least for the kind of loops that we have looked at, it was actually pretty fast. All right, so the first candidate is unlikely to actually be an inductive loop invariant, so we will get a counterexample from the solver. And it usually tends to be sort of at the boundary. So here it looks like it would still be inside the invariant, but it's just slightly outside. Now, and we would like to use these counterexamples to explore the space further in order to generate the next candidate invariant. Now, these counterexamples, however, are randomly generated by the solver. And we found that if you just use a single random example by the solver, we would be sort of exploring the space in just one direction, and the search would be biased, and we would actually not converge on a proper loop invariant. So what we found is that we need to generate some additional points, either by asking the solver for additional counterexamples, or, for example, by using the symmetry of the ellipsoids, where we found that very likely, so quite often, if we just use the symmetry, we will get points that are also counterexamples. Now, starting from these points, we will continue our previous procedure. So we will again do a simulation of the loop, because if these points are included in the invariant, then any points starting from those will also have to be inside the loop invariant. And then we'll continue the process. We will do another least squares fit. We will do another rounding, and we will hand off the next candidate invariant to the solver. And we will repeat this until hopefully eventually we will converge onto the final invariant, which in this case looks like the sort of darkest blue line. So for the kind of loops that we have looked at, so for instance, the one that I showed you was a simulation of a dynamical system. This approach works surprisingly well, also surprising to me. And part of this was the simulation-based generalization and the noisy polynomial fit. In case you're not sort of familiar with the literature, this was to our knowledge, the first technique that could handle nonlinear loop bodies. So where the loop body had nonlinear computations. And even for the linear loops, we could produce much tighter invariants than all the available approaches. Just as a side note, so this was only covering ranges, so lower and upper bounds. I did have some previous work that was trying to generate invariants that would deal with rounding errors, so not just the bounds, but the errors themselves. And this work actually relied on a technique like these kind of range invariants. So it was assuming someone would provide these. So we were kind of closing the gap, though I haven't really connected the dots fully yet. Are there any questions for this part?
So I have a question, which is maybe more in line with a suggestion. Can you go back a couple of slides? Keep going one more. And yeah, that. So here, your counterexamples, you're sort of at the mercy of the SMP
solver. Yeah.
So I think I may be misquoting this. Alice, I guess, is not here, but he was involved in some work. I think it was a 2014 Popple paper where he used optimization to find counterexample points. So he was actually looking for convex hulls in linear arithmetic. Mm-hmm. But so and in this case, because of the orientation of the ellipsoid, you can find a bounding box. I mean, I don't know whether this is a really good idea or not, but I mean, basically what he did is he shot a ray out in some direction.
Yep.
And then he wanted to find the furthest point out that was still a counterexample thing along that direction. So what if you sort of picked, I forget what they're called for ellipses, the sort of focal points, I guess.
Yeah.
Picked one of the focal points and just shot a ray toward one of the corners.
So it could be that this is quite similar to what we do when we use the symmetry. That said, we actually tried various different ways of doing these generalizations. And what we found is that it actually doesn't seem to matter all that much how you get the points. The point is that you have to have more than one. So if you take just a single one, then the search will just diverge and you will never converge on an invariant. So we have, for instance, tried to just asking the solver for a second counterexample that is not close to the original one. And I think we tried the third thing that I can't remember right now. And we just found it really doesn't matter which ones you use, as long as you have more than one.
I see.
Hi.
Yeah.
I'm Janu. I am a student of Lawrence and Tom. So I had a question about, is there a particular reason why ellipses are a good choice for floating point loop invariants?
So I guess I wasn't quite clear about this. So these ellipsoids will work for a certain set of programs. They will not work for any general floating point loop. And obviously they will only work for loops that actually have a loop invariant. So it happens to be, and there is a connection in control theory. So these invariants that we really find, they're Lyapunov functions that, for instance, in control would be used to show the stability. Unfortunately, all techniques to find these Lyapunov functions only work for linear loops. So as soon as you have nonlinear loops, you basically rely on some person to actually provide that loop invariant for you.
Okay, thanks.
All right, so it sounds like there are no more pressing questions. So now let me switch completely. And now we will talk about robots, and we will talk about, or I will talk about robots in this kind of simulation world. So you have a floor, you have a couple of rooms. The black tiles are walls where the robot cannot walk through. The robot is that gray box. There are some water tiles, which maybe the robot should avoid or maybe not. And then there are a number of items of interest. And what we were interested in is making it easier for end users or sort of non-experts in robotics programming to be able to program a robot. So some of this motivation comes from robots now frequently being used in sort of end user settings, maybe in a hospital setting where they will help to distribute some items. Now, the problem is that the standard language to program many robots, at least, is LTL, where I'm just showing here one command in a DSL, but that maps directly to LTL. So suppose that we want to pick one red item from the position 7.4, and 7.4 is exactly that tile. So basically want to pick that red item. Now, normally you would have to write down the command exactly as written here on the screen. But suppose that you actually are not so familiar with LTL, its syntax and or semantics, and you would rather use natural language. So for example, you may want to say, take one red item from 7.4. Now the system is not going to understand this because that command doesn't exactly match the LTL command. So what our system allows you to do is to provide one additional example where the example consists of you showing, so basically in our demonstration, you will just use your keys to move the robot to the position and to pick up that item that you're interested in. And what the system is going to do is it will produce a mapping between the natural language commands and the underlying DSL. So basically it will learn the corresponding DSL command. And by doing that, once we have the DSL command, then we can provide, or we can generate basically the plan for the robot to execute maybe in some real world setting. Now we will also use this mapping to generalize so that the next time you want to use a somewhat similar command, but not quite the same, you won't have to re-demonstrate it with an example. So the system will immediately understand, take every triangle item from 4.0. So underlying all of our system is a core grammar that maps to linear temporal logic. And we just use a DSL for convenience, but basically this is LTL over finite traces. So it's finite traces because in the robotics domain, you will usually have only some finite trace and not an infinite one. So basically we start off with this core grammar with our LTL, and then we will be expanding this grammar in 2 steps. So given some natural language commands, if the grammar doesn't understand that yet, because it's maybe not written in that core language, we will do first an interactive synthesis step to learn the corresponding LTL command corresponding to the natural language command, such that we can create the plan for the robot to execute. Now, in a second step, we will try to use a step that I'm calling grammar expansion in order to expand our initial grammar so that when the next similar command arrives, we don't have to go through the synthesis loop again, but we can immediately go and create the plan for the robot. So let me give you again at a high level an idea of how we do the interactive synthesis. So we're given one example, one trace. So this is just a trace of the steps and the actions, like picking up a red circle item, and the natural language command that the user gave initially. From this, our system will generate a number of candidate LTL commands that we will try to disambiguate interactively with the user. So basically, we will ask the user a couple of questions in order to narrow down the candidates just to a single one that is hopefully going to be the one that the user initially wanted. And that's the one that will then be used for the grammar expansion. So before we can generate these candidates, we actually need to do a step first, because if you have worked on synthesis, you'll probably know this. Just from a single example, you won't be able to generalize enough to actually find the right set of candidates. And in particular, what we need is our negative examples. So we have one positive example of what the robot should do, but we also need to get a number of negative examples. Now, in the robotics domain, it's a bit difficult to ask people to demonstrate what the robot should not do. So we generate these examples automatically using 2 principles. The one we call the principle of no excessive trace. So we take every prefix of the demonstrated example, as a negative example because we assume that the user wouldn't do more work than necessary. So basically, we assume that any such prefix would be insufficient to actually achieve the task. Somewhat similarly, the second principle of no excessive action will assume that no simpler action than the one that the user has demonstrated would also not be sufficient to achieve the task. So we will basically use any simpler action than the one demonstrated as a negative example as well. So then we have a set of examples. And from these, we will then generate candidates using max SMT. So basically the core synthesis in our case is using max SMT, where max SMT is an optimizing SMT procedure. So for max SMT, we can specify a number of hard constraints. So those are constraints that definitely have to be satisfied. And these are basically the constraints that that the candidates have to be consistent with our positive and negative samples. And then we use the optimization part of max SMT to encode soft constraints that will introduce some bias towards the natural language command that the user introduced. And in our example, we'll, for instance, get these 4 candidates. So we'll repeatedly ask the solver for one candidate formula after another, up to some fixed bound. So, and then from these ones, we have to figure out which one is the right one that the user actually wanted. And we will do this with a disambiguation loop. And for this, we will present the user with some simple, very simple worlds, such as this one. And normally the robot would actually move in the example, but I'm here just showing the arrow to demonstrate that the robot would have moved and picked up the green item. And the system will ask the user, is this what you wanted? Well, in this case, well, we wanted the red item, so this is not what we wanted. So this will eliminate one of the examples. Then the system will generate a second world where it picks up one of 2 red items at the corresponding position. And here we will say, yes, this is what we wanted. We wanted 1 item. And this will eliminate 2 of the candidates so that we will have now identified one of them that is then returned. And then we will use this one to do the grammar expansion. And for this, we are using a semantic parser to find a mapping between the natural language command and the underlying LTL specification. So for instance, there is a mapping between the constants 1, the colors red, and the positions. And what this mapping gives us is a new production rule for our grammar. Basically, we have our core grammar, and with each of these mappings, we're going to add 1 new production rule. And this gives us a generalization because basically our command with take some number of colored items is now going to work with any number and with any color, and also with any position. However, that's not the only mapping the semantic parser can find. It can, for instance, find a mapping between sort of the whole 3 words, because there is a quantified item category in our grammar. Now, this is you can think of this as a bigger generalization than the previous production rule, because this quantified item category is more general than just picking some number of colored items. So this would, for instance, also be able to generalize over different shapes and not just different colors. So again, we will add these two new rules such that in the future, the system will understand similar commands as well. Now, the way we envision this to work is such that in some setting, maybe think of a hospital, you can train the system gradually with these examples to understand sort of the specific language that you have in your context. So for instance, if your task is to distribute items of different colors from some particular location to the 4 corners of the world, you can do that with our system that is called LittleTalk, that I forgot to say. So you would first teach it to take one particular color from some location to one corner, where 1, 1 is one of the corners. So for this, you would have to specify the trace and use the interactive synthesis. Now, in the second step, you could then apply the same command for all the different colors and the different positions, and this would immediately work. Now, you could say that this is still a little bit awkward for an end user to write. So we do have some ongoing work that would allow somewhat still expert user on the underlying language to redefine this command, the long one, into just a short command like this. That would also come with some generalization similar to the semantic parser that I have shown you before. So that in the future, people could just say distribute colors from some particular location. Are there any questions for this part?
I mean, this reminds me a lot of the work that Ishil students did with regular expression. So I didn't quite understand. So how do you map right now to the grammar? Do you also use semantic parsing also?
Yes, so we use a semantic parser in a principle similar way than Ishil, but from my understanding is Ishil uses the semantic parsers in the first step and then kind of doesn't come back to it and then continues with sort of the remaining synthesis. Where for us, the semantic parser is more tightly integrated. I don't know if that.
Okay, yeah. And I think, don't you have a problem with finding, I mean, how do you get the data to train this in a way that actually works? Like, what is the, how do you evaluate this? Because it's like, I mean, where do you get the real data to evaluate this?
So we don't have real data in the sense that, yeah, we don't have actually a robot sitting in some hospital. So for the first part, we have generated a number of tasks. And I mean,
by real data, I mean the sentences.
Like this is something we have essentially made up.
Okay.
Now, for just the interactive synthesis part, I mean, that is basically executing the SMT solver, and basically you have you have an example trace, you have a natural language command, you have the ground truth that you can generate yourself, and basically we're trying to measure, well, how close can you get, or how often do we actually get the ground truth that we wanted to. For the second part, the ongoing work, we have already done some user studies where we have asked users to implement these kind of tasks that we have given them. And we have some groups, we have shown that they can use this kind of generalization, and others we have not. And at least in the preliminary studies, we have found that somewhat surprisingly, people always thought that they're not using the generalization, but they were actually using it. So they were benefiting from it, even if they weren't necessarily aware of it.
Thanks.
All right, I can take some more questions, but before that, I would like to thank all the students and all the collaborators that I've been working with. And yeah, that's sort of the last slide. Are there any more questions?
So I guess, I mean, I'm asking about this natural language because I'm interested. I mean, Tom and I are eventually doing something related to this, I guess. Like the part to understand of these techniques with natural languages, like what is a practical setting? Like how do we get what people actually write as sentences? And so so I think Ishil told me that now they have, for these regular expressions, they have a new paper after the semantic parsing one, where they figure out how to generate, with some NLP people, they managed to get a lot of data, like actually millions of examples, so they can actually use some deep technique instead of semantic parsing, and that gives better results. But I think for regular expressions, I can see how people will do it. Like you can come up with something that fairly reasonably maps English language to regular expressions people might write. But in this domain, it seems very tricky, right? To like, yes. I mean, do we have examples of some people say in English what they want? Like, can you mine requirements, for example?
So we actually, by using just as a standard semantic parser, we do not need a lot of data. We don't need any data to learn. And actually, we didn't want to learn just one kind of mapping because our understanding was that in different contexts, you may want to use a different language. So something you have learned in one context may just not work for the second group. So that's why our motivation was that you can basically have the system learn the language that you are using in your group. So our setting from the very beginning was that we do not actually want to have, or we don't need that training data. That said, programming robots with natural language is not a new thing. So there have been efforts before. Most of them focused on sort of a structured natural language. So you would have still a very fixed way of how you would have to phrase things. That you don't necessarily have with our system, because you can basically teach the system your particular jargon, if you wish. But that's probably somewhat specific to the robotics domain, and I'm not sure that would probably not generalize to other domains.
You should check my colleague. I can write in the chat his name, but he has some work.
So if you send me an email, then I will actually have it later too.
Okay, I'll also let me find it. Yeah, he's been doing some work also where they do demonstrations like with figurines. They move them on a fake board and then yeah, so it might be relevant. Cool. And so I guess my other question is what's next?
What's next? Well, I would like to do the approximation for not just numerical, so the automated approximation, not just for numerical kernels. So actual real end-to-end programs. I mean, that said, the numerical kernels are already relevant, say, for an embedded controller. But say if you have some health application, then maybe combining some neural network with some sensor processing or something like this, then this is something that's sort of out of reach today. But I think there is quite a lot of potential to save resources.
So another thing that we are doing with Tom is some synthesis work related to, basically we're trying to synthesize abstract transformers. And we were trying to adapt some of what we do. So right now we use Sketch as our base tool for what we are doing. But at some point we wanted to do something related to floating points operation. And we kind of ran out of tools. So there isn't quite something similar. So it's like, since you're in the area, what do people do there, if anything?
In terms of abstract domains?
No, for synthesis. Like if I want to do something like Sketch or Rosette or whatnot, and I have to deal with more complicated numerical domains like floating point. Like is there anything?
I'm not aware of any tool that can handle floating points. Now, I assume something like Sketch should be probably relatively easy to extend because obviously you can just use a floating point theory, basically.
Nah, but it's not actually, because that's kind of like, I think Armando has a bunch of people that have been trying unsuccessfully.
Okay. I mean, that would have been my easiest guess, basically.
Well, because Sketch doesn't use any theory. It's entirely in SAT.
I see.
It's basically, that's the reason it works, is because it bounds everything. Like even the integers are not actually integers. They're like 6-bit vectors.
Yeah, then you're probably screwed with floating points. I mean, that would be my easiest, what I would have thought would be the easiest solution. I'm not aware of any synthesis tool that can handle floating points as of now.
Then
sorry.
I'm aware of the same things. Yeah, I don't know much in this. I know like it's a bit of a different community, because it's like sometimes these FMCAD people, maybe they put something and I don't read those papers much. So I just wanted to make sure I was not missing much.
I can send you a link to a website that originated from a benchmark set for floating point expressions. There was also last year a set of talks on sort of the floating point verification kind of optimization domain. I presented, for instance, this loop invariant synthesis. So that may give you at least a bit of idea of who's working on what. Other than that, I mean, I am happy to answer some questions as well. I mean, offline too.
your middle project here, this floating point loop invariant synthesis, is doing floating point synthesis. So to what extent could that technology be harvested to do something else that you're not, that, I mean, you've sort of packaged it up so that it handles these loops, and is it really restricted to only these ellipsoid loops, or?
So we had some initial trials with higher order polynomials, for instance, and I have a hunch that it should work as well. There was just one particular piece missing that we just didn't have a Python library for, as for all the rest. So we haven't explored that further, but I do think that this can generalize further as well. Now, I don't know exactly what you have in mind, so I can't really say whether it's going to work for that. But in general, for many of these invariant techniques, I think the best way is to try to abstract the actual floating point arithmetic, if at all possible, so that you do not have to rely on some exact reasoning about floating points. If only for scalability reasons. Because if you are able to abstract it, say, with real arithmetic and some of these error bounds on the top, then you may also be able to use continuous reasoning that usually is also more scalable. Just trying to reason about the individual floating point bits, at least for us, was usually a bad idea.
Sure, but I think, I mean, we were actually down a little bit lower. We weren't doing anything that had anything to do with quadratics. It was linear functions.
So for linear arithmetic, there's, I mean, so I don't exactly know what you're doing, but if you look at the abstract domains, such as affine arithmetic, they're at least, I mean, for linear operations, they will be the best that you can probably get. And that works reasonably well. I mean, this is also internally what we are using. So we use affine arithmetic, and then we approximate the nonlinear operations in the accuracy analysis.
Yeah. Okay, thank you.
So if you have some draft or some initial paper, so I'm also happy to look at that if you are looking for some additional suggestions.
Well, thank you so much for coming all the way from Germany to give this talk.
Yeah.
It's almost bedtime there.
Thank you.
Well, I am very much hoping that my husband has managed to bring my kid into bed, so I don't have to do that now.
That's good. So hopefully that worked out. Okay. Anyway, thank you so much, Eva. It was a very interesting talk, and see you.
Thanks for the invite.
Yeah, thank you for coming. Bye-bye.
Bye-bye.